Physicists say that the universe had its origin in an event known as the Big Bang approximately 13.7 billion years ago. However, the question that arises is what caused that explosion and why it occurred. Over time, we have been researching and studying the science and history of our universe, and the Big Bang has been the predominant explanation for everything we have observed. Countless studies and thousands of scientists have worked on the research. The data collected has always supported the Big Bang theory as the main explanation for how the universe was formed. According to this theory, dark energy is a form of energy even more abundant than galactic energy, and is considered the anti-gravitational force responsible for the continued expansion of the universe. The Big Bang theory has been the cornerstone of cosmological studies and has shaped our understanding of the universe's origins and evolution. Science today is very different from what it was in the past, and with technological advances, new theories emerge. Many times we discover that things we thought to be absolutely true are far from being so. Michio Kaku has raised the official debunking of the Big Bang. This is because the James Webb Space Telescope has detected 750 new galaxies that look nothing like what was expected. This raises a new perspective and leads us to delve deeper into how the James Webb Space Telescope is changing our understanding of the universe. Join us on this incredible journey beyond the far reaches of the observable universe to discover more details about the immense number of new galaxies that have been discovered. These discoveries compel us to rethink the very foundations of cosmology and the dynamics of the universe. If you're interested in keeping up to date with news from the universe and its surroundings, subscribe to our channel. Be sure to like this video, share it to reach more people, and turn on the notification bell. The images of new galaxies captured by the James Webb Telescope are absolutely stunning. In a single image, we can see hundreds of galaxies altogether, and the beauty and power of these photos are stunning, something that cannot be overlooked. However, what seems to amaze the average person is precisely the opposite for researchers. These images are amazing to them, but they do not match what scientists expected to see based on their theories. In fact, many more galaxies are being seen than expected, and these galaxies are different from the rest. They are smaller than imagined and have a truly remarkable age. These surprises are generating some panic among scientists. There is even an article that begins with the word panic in its title, which shows the seriousness of the situation. These galaxies are nothing like they were supposed to be according to established theories. For a long time, scientists have proposed the Big Bang theory as the main explanation for the origins of our vast universe. According to this theory, approximately 13.7 billion years ago, the universe began its existence through some kind of mysterious cosmic event. However, these images challenge the definitive story of the birth of the cosmos as previously understood. The discrepancy between theory and observation urges a re-evaluation of long-held cosmological models and assumptions. The striking images captured by the James Webb Telescope have challenged our understanding of the origins of the universe. Specifically, these images directly contradict the Big Bang hypothesis, which has long been considered an unquestioned truth by cosmology theorists. The galaxies captured in these images appear to be small, smooth, old, and numerous compared to the predictions of the Big Bang hypothesis. The fact that the observed galaxies are 2 to 3 times smaller than similar galaxies imaged by the Hubble Space Telescope completely defies the expected behavior in an expanding universe. According to the hypothesis, as the universe expands, objects should appear larger as distance increases. However, these James Webb observations show galaxies that defy that expectation. Moreover, the smoothness of these galaxies is totally unexpected. According to the Big Bang theory, galaxies should show irregularities and variations in their structures due to the dynamics of their formation and evolution. However, the images reveal unusually smooth galaxies without the level of complexity and roughness that one would normally expect to see in galaxies of their age. This defies the expected time sequence for the formation and evolution of galaxies within the framework of the Big Bang theory. These findings necessitate a rethinking of the mechanisms of galaxy formation and the influence of cosmic forces over billions of years. At the beginning of the universe, all matter, energy, and building blocks of the cosmos were compressed into an extremely concentrated point called a singularity. At this point, the density reached an infinitely high value due to the extreme compression pressure of matter and energy. The concept of singularity is based on our current understanding of the laws of physics, especially the equations of general relativity proposed by Albert Einstein. Within the singularity, all matter and energy in the universe existed in an extraordinarily compressed form. This extreme density implies that an enormous amount of mass and energy was concentrated in an infinitely small space. Under extreme pressure and density conditions such as those present in the singularity, the heat is unimaginable. The temperature within the singularity would exceed any temperature observable or reproducible in our current understanding of the universe. The energy stored in this hot, dense point was a seed from which the entire universe, as we know it today, originated. The singularity marks the beginning of the universe, the origin of everything in our cosmos. After the initial singularity, the universe began its journey of expansion and inflation. This process occurred over approximately 13.7 billion years, giving rise to the universe as we know it today. The expansion of the universe began with an extraordinarily rapid burst known as cosmic inflation. During this phase, the universe expanded at an unimaginable speed, far exceeding the speed of light. It is as if the very fabric of space stretched and stretched, pulling everything within it. Cosmic inflation played a massive role in the formation of the large-scale structures of the universe. It smoothed out irregularities, homogenized the distribution of matter and energy, and paved the way for the subsequent formation of galaxies, stars, and other cosmic structures. This period of inflation is crucial for explaining the uniformity observed in the cosmic microwave background radiation. As the universe continued to expand, the rate of the expansion gradually slowed. It is important to note that although there was rapid cosmic inflation in the initial period, the universe continued to expand at a measurable rate. This steady expansion is known as the cosmic expansion or the expansion of the universe. Scientists have observed the effects of this expansion through various observations, such as the redshift of light from distant galaxies. Redshift indicates that as the universe expands, light waves are stretched and shifted to longer wavelengths, moving them towards the red end of the spectrum. During this expansion, all the stuff that makes up our universe was compressed into an incredibly small volume. It was clear that matter could not survive in such a compact space, so transformations occurred as the universe expanded and cooled. Particles such as protons, neutrons, and electrons began to interact with the light and energy around them. These interactions played a key role in the formation of matter in the universe during the first minutes after the Big Bang. This process is known as nucleosynthesis and is fundamental to the creation of the elements that form the basis of all matter in the universe. Chaotic and disrupted galaxies due to multiple collisions were expected to be observed, but the images captured by the JWST tell a different story. Instead of chaotic galaxies, the images reveal well-organized disk and spiral structures similar to the galaxies we see in today's universe. This unexpected observation challenges the idea that mergers are a common process in galaxy evolution. If these new galaxies have not experienced many or any mergers, it becomes unlikely that small galaxies will grow and become hundreds of times larger as expected. This implies that these galaxies were never small originally. Furthermore, the optical illusion created by the expanding universe hypothesis, where objects appear to be smaller due to expansion, does not hold in this case either. Therefore, what we have believed so far turns out to be a falsehood. In addition, the age and abundance of galaxies revealed by the James Webb Space Telescope also challenge the validity of the Big Bang theory. The JWST is equipped with filters that allow imaging in the infrared part of the spectrum, which facilitates the study of the colors of these galaxies. By analyzing these colors, astronomers can estimate the age of stars and galaxies. These new insights prompt a reconsideration of the processes that have shaped the universe. One of the fundamental mysteries that have fascinated humanity for centuries is the origin and evolution of the universe. From ancient myths to modern scientific theories, humans have continuously sought to understand how everything began and how it has developed over billions of years. Today, our understanding is largely shaped by the Big Bang theory, which posits that the universe began as an infinitely small, dense point and has been expanding ever since. The Big Bang theory emerged from a convergence of theoretical physics, observational astronomy, and cosmological principles. It suggests that approximately 13.7 billion years ago, all the matter, energy, and space-time of the universe originated from a singularity, an infinitely small and hot point. This singularity underwent rapid expansion, known as cosmic inflation, during the first fraction of a second after its birth. This period of inflation smoothed out irregularities and set the stage for the subsequent formation of galaxies, stars, and other cosmic structures. As the universe expanded and cooled, the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, separated and began to govern the interactions between particles and matter. This allowed for the formation of protons, neutrons, and electrons, which eventually combined to form atoms of hydrogen and helium. These primordial elements were the building blocks from which stars and galaxies would later emerge. The study of the early universe and its evolution has been revolutionized by advancements in observational technology, such as telescopes and satellites. One of the most significant instruments in modern cosmology is the James Webb Space Telescope, JWST. Scheduled for launch in 2021, the JWST promises to provide unprecedented insights into the formation and structure of galaxies, stars, and planetary systems. Unlike its predecessors, such as the Hubble Space Telescope, the JWST will operate primarily in the infrared spectrum. This capability will allow astronomers to peer through cosmic dust clouds and observe the birth of stars and galaxies that are otherwise hidden from view. By studying the light emitted by these celestial objects, scientists hope to unravel the mysteries surrounding the early stages of cosmic evolution and the conditions that gave rise to the universe as we know it today. The JWST's infrared sensitivity will also enable astronomers to probe the atmospheres of exoplanets, planets orbiting stars outside our solar system. By analyzing the chemical composition and temperature profiles of these distant worlds, researchers aim to identify potentially habitable planets and even detect signs of life beyond Earth. This groundbreaking research could fundamentally alter our understanding of the prevalence and diversity of life in the universe. In addition to its scientific objectives, the JWST represents a testament to human ingenuity and international collaboration. Developed through a partnership between NASA, the European Space Agency (ESA), and the Canadian Space Agency (CSA, the telescope embodies the collective efforts of thousands of scientists, engineers, and technicians from around the world. Its construction and assembly involved cutting-edge technologies and innovative solutions to overcome the challenges of operating in the harsh environment of space. The JWST's primary mirror, composed of 18 hexagonal segments, will have a total surface area significantly larger than that of the Hubble Space Telescope's mirror. This increased light-collecting area will enhance the telescope's sensitivity and resolution, allowing it to observe fainter and more distant objects with greater clarity. Combined with its advanced suite of instruments and detectors, the JWST is poised to revolutionize our understanding of the cosmos and address some of the most profound questions in astrophysics and cosmology. Among the key scientific goals of the JWST is to investigate the formation and evolution of galaxies throughout cosmic history. By observing galaxies across different epochs, from the early universe to the present day, scientists hope to trace the processes responsible for their growth, structure, and diversity. This includes studying the role of dark matter and dark energy in shaping the large-scale structure of the universe and influencing the motion of galaxies over billions of years. Another major focus of the JWST's mission is the study of star formation and stellar evolution. By observing young, newly formed stars and their surrounding protoplanetary disks, astronomers aim to understand the conditions under which stars are born and the factors that determine their lifespan and eventual fate. This research is crucial for unraveling the complex interplay between gravity, radiation, and magnetic fields that govern the birth and death of stars throughout the cosmos. In addition to studying galaxies and stars, the JWST will investigate the properties and atmospheres of exoplanets orbiting distant stars. By analyzing the light passing through the atmospheres of these planets during transit events, scientists can identify and characterize key molecules such as water vapor, carbon dioxide, and methane. These observations will provide insights into the composition, climate, and potential habitability of exoplanets, laying the groundwork for future missions to search for signs of life beyond Earth. The search for habitable exoplanets and extraterrestrial life represents one of the most profound questions in astronomy and astrobiology. While the discovery of Earth-like planets within the habitable zone of their parent stars has sparked excitement and speculation, the JWST's advanced capabilities offer unprecedented opportunities to study these distant worlds in detail. By examining their atmospheric compositions and surface conditions, scientists hope to identify potential biosignatures, indicators of biological activity that could hint at the presence of life. Beyond its scientific objectives, the JWST embodies humanity's enduring curiosity and quest for knowledge about our place in the universe. From ancient civilizations gazing at the stars to modern astronomers exploring distant galaxies, the desire to understand the cosmos and our origins has driven scientific discovery and technological innovation. The JWST represents a new chapter in this journey, a chapter that promises to reveal new insights into the nature of the universe and our place within it. The JWST's ability to observe the universe in unprecedented detail and sensitivity will also contribute to our understanding of fundamental physics and cosmology. By studying the cosmic microwave background radiation, the residual heat left over from the Big Bang, scientists can probe the earliest moments of the universe's existence and test theories about its initial conditions and subsequent evolution. This includes investigating the nature of dark matter and dark energy, which together constitute the vast majority of the universe's mass-energy content, but remain elusive and poorly understood. Furthermore, the JWST will play a crucial role in studying the formation and evolution of planetary systems beyond our own. By observing protoplanetary disks, the swirling clouds of gas and dust from which planets are born, scientists hope to unravel the processes that lead to the formation of diverse planetary architectures, including rocky planets like Earth and gas giants like Jupiter. These observations will provide insights into the conditions under which planets form and the factors that shape their orbits, compositions, and potential for hosting life. The JWST's ability to peer through cosmic dust clouds and observe the infrared emissions from young stars and planetary systems will also shed light on the mechanisms of star and planet formation. By studying the interactions between newly formed stars and their surrounding protoplanetary disks, scientists can gain insights into the physical processes that drive the accretion of matter and the evolution of planetary systems over time. This research is crucial for understanding the diversity of planetary systems in the galaxy and the conditions that give rise to habitable environments. In addition to its scientific objectives, the JWST represents a technological marvel and a testament to human ingenuity and collaboration. Its development and construction involved thousands of scientists, engineers, and technicians from around the world, working together to overcome the challenges of designing, building, and launching a cutting-edge space telescope. The JWST's instruments and detectors, including its advanced infrared cameras and spectrographs, represent state-of-the-art technology capable of capturing detailed images and spectra of celestial objects billions of light-years away. The JWST's primary mirror, composed of 18 hexagonal segments made of lightweight beryllium, will have a total surface area significantly larger than that of the Hubble Space Telescope's mirror. This increased light-collecting area will enhance the telescope's sensitivity and resolution, allowing it to observe fainter and more distant objects with greater clarity and detail. Combined with its advanced suite of instruments, including a near-infrared camera, a mid-infrared instrument, and a near-infrared spectrograph, the JWST will enable scientists to address some of the most pressing questions in astronomy and cosmology.